Welcome back to the office hour for the RC design class. And today I'm mainly going to go through the past few exams, and especially on the problem that related to what we have covered so far, and kind of give us a feel about what's going to happen in the final exam. All right. So first thing first, let me start sharing the document. And you should have both documents on Canvas. If you don't, please double check and make sure you have them. Okay. So now let's take a quick look at the first problem, right? Compute effective flange width BF for monolithic cast-in-place concrete beams indicated below. This part, we actually have done it in the first exam, so I don't think we'll test this again. But just out of curiosity, right, you should know that this is basically testing the BEFF, the effective flange width. And we know that for midspan T-beam, that's one set equation. And for the end L shape, there's another equation, right? So there are two equations for this, and that's A and B, right? That's A and B. A is right here, B is right here. Now, next one, circle the correct response below. Adding compressive reinforcement. This again, we tested in the first exam, right? This is significantly increase the ductility. All right. 1C, this is related. So let me highlight this one, okay? This is related. For one-way slab, reinforcement is placed in a horizontal direction perpendicular to the slab span direction to resist the stress due to what? Now, blah, 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 very long, right? The keywords are first thing, one-way slab. Okay, it is one way. What do you mean by that? Well, we have two directions in one-way slab. One is longitudinal direction, and the other is transverse direction. Okay, so what is longitudinal direction? Longitudinal direction is the span direction. So when you see the span direction, you realize that that is the longitudinal direction. Okay, so the question is asking you, the reinforcement is placed in horizontal direction perpendicular to the span direction. That means that it is transverse. It is transverse, right? Because transverse span direction, it is perpendicular to the span direction or to the longitudinal direction. So this is asking the reinforcement along the transverse direction. What's the reinforcement along transverse directions for, right? So basically it's for shrinkage and temperature. So C is the correct answer. C is the correct answer. All right. Now 1D, this again is related. I'm just going to highlight this. Okay. List 3 of the requirements given the ACI 318 code for using the ACI moment and shear coefficient. So this is testing the requirement for moment coefficient. There actually are 6 requirements. So you only have to list the 3 out of the 6. All right. Okay. For the next one, the ACI 318-14 code start a maximum spacing for vertical stirrups. Now, shears also will be included for this exam, right? So let's take a look at this. Maximum spacing for vertical stirrups, right? So this is 14, and in the exam, you'll see 19, but not much of a differences, not much of differences, okay? Now, D over 2 or 24 inches, right? So that's one, the maximum spacing requirement. D over 2 or 24 inches, unless VS exceeds this one. Yeah, but not really. D over 4 and 12 inch, unless this one. So yes, but not really. There are other 2 requirements, okay? There are other 2 requirements, okay? So what the other 2? The 200 and there's a 50 underneath the division line there. So go back and review that, okay? So that's not it. So this one, shear, should be none of the above, okay? Now, which of the following is not the mechanism of shear transfer reinforced concrete beam without shear reinforcement, okay? Keywords, not a mechanism, okay? And without shear reinforcement, okay? So the shear contribution have 2 parts. One is the reinforcement part and the other is concrete part, okay? Now, among the reinforcement part, we all know that that's for reinforcement. This is asking without reinforcement. So let's take a look at the component without reinforcement. What are those, right? Aggregate interlock, sure, there are aggregate interlocking, right? Dowel action, yes, there are dowel actions, right? And shear and uncracked compressive zone in the top concrete compressive, remember? So those 3 are in there. So which are not there, the adhesion is not there, okay? The adhesion is not there. All right, okay, so 1F, answer is B. Okay, 1G, the ACI code requires the use of shear reinforcement in beams when, okay, again, the ACI code requires the use of shear reinforcement in beams when what? When VU exceeds VBC, yes, but this is not necessary conditions, right? This is, you have to, when you see this immediately, right? But B 1/3, I don't know where this 1/3 coming from. This is makeup number, right? When VU exceed 1/2, half of VBC, yes, because at this point, we need to provide some reinforcement, a very small amount of reinforcement in it. Remember? So C is the right answer, okay? C is the right answer. All right, moving on, 1H. The general layout for the shear reinforcement, the beam shown below is most likely to be A, O reinforcement, O shear reinforcement laid out like this, B in the middle, C two sides of it, D heavily in the middle, a little bit less on the sides. Which one? To understand this, first thing you ask yourself is what does the shear diagram look like? What does the shear diagram look like? Now, I don't have anything to draw on it, but you think of it, right? So at the support, I have the maximum shear, which is P, all right? Then I go along, all of a sudden here, I drop to 0. And then it will stay to a 0 value and then drop to another P and then stay at the P. In the middle, there is no shear force at all. There is no shear force at all. When there's no shear force at all, you don't need to provide anything, right? So that's C right here. That is C right here. Okay, so C is the correct answer. All right, 1-9. Draw the location of a critical section. Critical section, these are the keywords, right? Critical section for determining shear design for each of the following conditions. And label the distance of the critical section appropriately. Label the distance, okay? Now, on the left, this is beam column. So you know that it is a 45-degree of angle crack like this, okay? 45-degree, you see my mouse cursor, a 45-degree angle crack like this, 45-degree angle crack like that. And distance is depth D away from the interior side of the support. Distance D away, okay? So that's for the one beam column joint. For the right-hand side one, somehow it's not showing clearly, but I have a concentrated force. Concentrated force. For this one, if it's concentrated, you have to have a concentrated force location at concentrated force at the critical section, okay? So that's another one. That's another one. So this one, easy, right? You should be able to do it. Now, problem number 2, moment coefficient and slab design. Moment coefficient and slab design. Now, I want you to think this way. We're only going to have 4 problems in the final exam. 4 problems in the final exam. Now, what we have learned after the first exam, we have learned shear, which we just covered a little bit, and we have learned the one-way slab, the moment coefficient, and the deflection calculations. And last thing but not least, we'll talk about it, which is tomorrow, the column design. The column design, right? So you think of the 4 problems we're going to have, most likely you're going to see one big problem for shear, one big problem for moment coefficient and one-way slab, and one big problem for deflection, and one big problem for column, right? So that's naturally 4 problems. Let me repeat in case you will watch this at home and you want to understand what will be on the exam. So we have covered 4 main things after the first exam. First thing, we talk about the shear design, right? And the second thing, we talk about a one-way slab, the moment coefficient. They're kind of together because we need to know moment coefficient to know how much moment for that one-way slab, right? And then the third thing will be deflection, right? Where you find ICR, IGT, find how much deflection you need. There are long-term deflection, short-term deflections, right? And the last but not least, the column design, which we'll talk about it. So naturally, you would think that there will be 4 problems in the final exam, all right? But enough said, let's take a look at this problem, right? 4-span, one-way, solid reinforced concrete slab shown in the figure, built integrally with support. Built integrally with support, okay? This is keyword, integrally with the support, poured together, okay? Poured monolithically. The service dead load is self-weight only, 150 pounds per cubic foot, right? Because it's a 1 foot of unit strip, so 150 pounds per square foot, okay? Now the service live load, 80 pounds per square foot, and 5,000 PSI concrete and with a grade 60 reinforcing steel, all right? So you look at this, first thing first is that they call it transverse section, okay? But not necessarily the transverse span, okay? This is actually longitudinal direction, but transverse section because you're looking at the cross section right here, okay? Now, if I look at this figure right here, first thing I see is on the left side of it, this is a column. This is a column. This is not a end, okay? This is a column. So why this is so important? Because if you recall, in the moment coefficient table, it's a very messy table a few weeks back, we talked about that. There were 3 rows. 3 rows of coefficient numbers, right? And this is a column, so there's a 1 row that we're going to go with, and you will see which row that is, okay? Once you have that row, you can have all these coefficients mapped out, okay? But before we go there, right, so estimate the appropriate slab thickness using the ACI 318 code. How do we estimate the thickness of the slab? There is one equation in the one-way slab lecture. Let me repeat, and I know you're going to take some time to go back to that lecture notes to find that equation, but in the one-way slab example, we showed one equation to estimate the slab thickness and use that equation. And note that there's a sentence saying here, select an integer value for your design slab thickness. What do I mean by that? If your calculated slab thickness is 5.5 inch, you say 6 inch. If your calculate slab thickness is 6.1 inch, you say 7 inch. If your calculated slab thickness is 7.00001 inch, you say 8 inch. Okay, you go above, now below. Okay, you want the thicker slab thickness. Okay, thicker slab thickness. So that's that for H. Now determine the appropriate ACI moment coefficient Cm for the location indicated below. That means I need to have a negative value here, positive here. So A is negative, B is positive, C is negative, D is negative, E is positive, F is negative, so on and so forth, right? You don't see a sign here, so don't worry about it, okay? Don't worry about it, but you have the value here. Now, how do you choose these? How do you choose these? Remember, it's got to be one of the 3 rows we talk about it, and this is a column slab, so you know which row you're going to pick, and you find a number, okay? You can find a number. All right, so that's for 2B, basically just read out from the table, no difficulty there. And then it says that using the ACI moment coefficient from problem 2B, using one of these values, okay? Determine the slab design moment MU, including the signs at the locations indicated below, including the self-weight of the slab when you select the problem 2A in your calculations, 5-point total. All right, so several things. Use moment coefficient from problem 2B, meaning you pick the number from here, the answer you already selected in 2B, okay? And remember that, what is the moment? So before you do everything, you start thinking, I know this, MU is some coefficient. I'm making things up here, okay, folks? This is not the right answer. I'm making things up here, okay? I'm just going to assume that maybe for B, I'm picking 1/16, okay? I'm making things up here. I'm making things up, okay? 1/16, and the number after it is omega u, ln squared, right? Now for B, let's take a look, right? Let me roll up a little bit. For B, which is right here, and that is a middle span of 12 feet. So I know at this point, my ln, ln is 12 feet, right? Is that right? No, your ln is not 12 feet. Why is that, Bob? You're tricking me. No, I'm not. Because remember when we say ln, it's called clear span. So you have to reduce this by remove the thickness of the column, which is the 6 inch right here, and another thickness of the beam right here, which is another 6 inch. Okay, so this is clear span is 11 foot. Clear span here, 12 foot. And clear span here, 12 feet. Clear span here, 11 feet. Okay, don't forget. So this is actually 11 feet. All right, so first thing first, clarify is 11 feet right here. How about omega u? Omega u is applied loading. We all know it is 1.2 dead omega d plus 1.6 live 1.6 omega L. Now, what is omega d? Omega d is a dead load. What is dead load? The self weight only. So what is self weight? Self weight is 150 pounds per cubic foot, but we're talking about unit strip. Remember, it's a 1 foot unit strip, right? So this is actually 150 pounds per square foot. All right. So that is the dead load, and live load is 80 square pound per square foot. So you can calculate it and get your omega u. All right. And then once you have omega u, don't forget, this is in terms of pounds. You want to convert it back to kip. Okay. Do I need to do the number? You can easily do the number, right? So 1.2 multiplied 150 plus 1.6 multiplied 80, right? You got some number, get some kips, and there's 11 feet squared, okay? Don't forget squared. Then you divide the whole thing, by you divide the whole thing by 16ths, right? And you get some number. So let's just say, I again mix things up, okay? Let me do a quick calculation and try to get close, right? So calculator, so I have 1.5, sorry, 1.2 multiply 150 and plus a 1.6 multiply 80, I have 308. So 0.38, 308 and multiply 11 feet square. So 11 multiply 11 and multiply 0.308 and then divided by 16. So divided by 16 is 4.928. Okay, I'm just getting some numbers. So 4.928. All right. And this number right here is supposed to be the moment, supposedly to be the moment. So what exactly is the moment unit here? Don't forget the unit will be a kip foot, because it's moment, right? So you have a force, you have a distance, and this is per unit strip. So kip foot per foot, kip foot per foot. So that's for MUB. So similarly, you can pick the coefficient from one of the numbers and get MUD accordingly, What I want to emphasize is the unit, okay? Kip foot per foot, kip foot per foot. Okay, all right, so that one is problem 2C, okay? Now problem 2D, design the flexure reinforcement at midspan of location B. Perform the necessary code checks for your design. Oh, all right, so where are we at? We're here at B, span right here, B, okay? So I'm going to design a longitudinal reinforcement flexure, okay? Flexure. That means I am going to do a cross-section cut, and this cross-section is going to be, a foot of a slab, okay? So this is going to be 1 foot of cross-section, and this is my cross-section view, okay? And 1 foot, and I have some reinforcement. I don't know what it is, right? I don't know what it is, but I need to design for it. And the applied moments here, mu, as I show from here, is 4.928, okay? 4.928 kip foot per foot. So that is your design moment. And then you pull out your lecture notes on the one-way slab design and go through the process, and then you should be able to design for it. Okay, design for it. So that's 2D. All right. So moving on, and after I did the longitudinal reinforcement, the problem is asking me to do the transverse direction shrinkage temperature. So how do I do shrinkage temperature? Remember, there's a maximum spacing, and there's equivalently a minimum amount of reinforcement need to put in the section, right? There's a 0.0018, 0.0012 of AG, where AG is the cross section area. Again, this is not so bad. You can go back to the lecture notes and find out, okay? Go back to the lecture notes, find out. All right, so that's problem 2, okay? Problem 3, I have this irregular section. I'm going to find a bending moment. Fortunately or unfortunately, we covered this already in the first exam. So you most likely will not see this problem. But still, if you want to calculate it, you're interested, let me know. We can discuss about it. All right. Now, design for shear. Now, this problem is very interesting. Okay. Let me say this. This is a very interesting problem. I won't say this is my favorite, but this is my second favorite. So you might see this in the exam. Okay. You might see this in the exam. All right, so the cast-in-place reinforced concrete beam below is subject to concentrated load as shown, where PU is 120 kips. The clear span is 20 feet. The self-weight can be neglected. Oh, good news. I don't have to worry about the self-weight, okay? No self-weight need to be considered. The beam is constructed with normal weight concrete with 4,500 PSI, yield strength of 60 KSI. Note that there's a 5.5-inch wide, a 10-inch deep opening along the length of the beam as shown. That means there's a hole in the middle of the section, All these words, blah, 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 is basically asking you that when you calculate this this shear design, when you're trying to find the shear design, you need to use a width, right? And there's a width called BW, right? BW. In this case, BW is what? Is 15 inches minus the 5.5, okay? The 15 inches minus 5.5. So in that sense, this is 5 and this is 14 divided minus 5, so 9.5 inch of BW, okay? Very important. Why, Bob? Why is this important? Because remember 2 lambda, which is a concrete VC, square root F prime C, remember the equation, and BW D, right? So you need a BW right here, okay? You need a BW here. And where you add it, you look at a D here. D is basically 30-inch minus a 2.5, right? So you got 27.5 inch of D right here, okay? 27.5 inch of D right here. All right, so you have VC, you have BW. I think things are looking pretty good, okay? But before you proceed, you think about it, right? I want to take a look at the diagram, shear diagram that is. So it is a simply support, it looks like it, right? So I have a half of support of PU over 2 on the left side. I have another half of support of PU over 2 on the right side. And this fellow, this shear diagram fellow looks like this. Half PU, and then I started go all the way here, and then drop down because I have a PU here, and then another half PU, right? So this is half PU on the left, and this is half PU on the right. And then in the middle, I have this half and this half that makes up to the total PU right here. So this is my shear diagram. Why do I need shear diagram? Or why am I even interested in showing this? Because yes, the shear direction for left span and right span is different, but the amount of shear that this span has to resist is identical. That is 60 kips. That means your VU, that is your VU is equal to 60 kips. 60 kips, okay? Not 120, but 60, okay? Why? Half of it, all right? So before you do anything, you know that I'm going to jump quickly to 4C, that is the stirrups design. I am going to design the stirrup spacing for a VU of 60 kips. I'm going to design a stirrup spacing for a VU of 60 kips, okay? So that is very important. That is very important for the shear design. All right. So from there, I go back to see VC. What is VC, right? You know that equation. That is the equation 2 lambda square root F prime C BW ds. You are tested for the knowledge of BW and the knowledge of ds, and that's it. All right. Determine the minimum area of shear reinforcement for this beam. Minimum area of shear reinforcement for this beam. Okay. So what is AV mean? Remember AV mean, there are 2 requirements, and there are also 24. Remember, have D, and also there are 500 or 200, and there are something blah 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 50. Remember, and all those are supposed to be in a table in shear design lecture notes. There's a beautiful table in the shear design lecture notes. You should be able to see it, and you should be able to find it. All right. So for C, it just provides stereo spacing. You basically design the whole thing using VU 60 kips. The only catch here is using number 3, 2-leg stirrups. It even tells you there's 2-leg stirrups. So area of number 3 per bar is 0.11 inch squared. And multiply 2 per stirrup, you have a 0.22 inch squared. Okay, inch squared. I think I'm right, but make sure you double check it. Okay, make sure you double check it. So that's supposed to be the area of stirrups equal to AS. Equal to AS. Okay, all right, so think about that and then put this into the thought when you design for the stirrup spacing, Note that in the shear design lecture notes, and I know most of you haven't reviewed yet, but when you review the lecture notes on the shear design, make sure that you understand there are 2 types of shear design. One is to design for a specific VU, like we're doing here in the exam. The other is designed for a varying VU, meaning the shear diagram is not constant. Now, in the exam, let me say this to save your time. In the exam, we will not ask you to design shear for a varying shear diagram, okay? Let me say this again. In the exam, we will not ask you guys to design for a varying shear diagram. Most likely, like this problem, we're going to give you a constant VU and ask you to design for stirrup spacing. All right. Okay. So that is for the stirrups, for the shear. Okay. All right. Moving on. I'm done with this midterm exam number 2, which will be part of the final exam. Any questions, folks? You guys here? So questions? Anything? Anything? All right. Okay, well, I'm assuming that I'm going very fast and you need time to digest. So go back and review this part. If you have any questions, email me and we can always discuss. Okay. And this is for the second exam, which will be part of the final now, okay? Which will be part of the final now. So let's go back quickly, right? Let me do some cleaning up, right? So you know the gist of it. So 1A will not be on the exam. 1B will not be on the exam. 1C might be on the exam. 1D might be on the exam, okay? All right, so this is for problem one, okay? And now moving on. 1E, I haven't finished this. Might be on the exam. 1F might be on the exam. 1G might be on the exam. 1H definitely gonna be on the exam. Definitely gonna be on the exam. 1I might be on the exam. Okay, might be on the exam. Okay. Now go on. This is problem 2. I would say definitely on the exam. We'll change the configuration slightly. We'll change the number slightly as well, but make sure you know how to do this because this will be on the exam. Okay. Will be on the exam. Now going back, number 3, see who is that? That is the irregular section, and I can guarantee you this will not be on the exam. This will not be on the exam, okay? This will not be on the exam. Now moving forward, and last problem, but not least the problem is a shear design, and I guarantee you this will be on the exam. Not exactly this configuration, not exactly this configuration, but definitely will be on the exam, okay? One hint. I am doing a beam like this, right? A rectangular with an opening in the middle. What if I end up with a T-beam or I-beam? What if I end up with this? I have reinforcement here, reinforcement here. How do I do this? Well, it's the same, right? The only thing changes that the BW is now the web width, the width of the web. Okay, the width of the web. Alrighty, so that's for this second exam. Like I said, if you don't have any questions, go back, please digest. And if you do, send me an email and we can talk about it. All right. Okay. Now the final exam from last year. Okay. Now keep in mind, this final exam we did last year is under the condition that everything is lump sum. We did all kind of problem in the final exam. Okay. But now in this exam, we will not have all kind of problem in this. So you see a lot of repeating problem. It's good for you because I might just take one of the repeating problem into consideration for the final exam, right? So let's take a quick look at this one. If this one is a one-way slab problem, then you should see moment coefficient, but you don't, right? Instead, you were asked to find out effective flange width, So that one is already covered in the first exam, so we will not have this problem, okay? Now for this one, for figure shown in problem 1A, the reinforcement placed horizontally in the slab. This sounds like a one-way slab problem, okay? Horizontally in the slab in the direction parallel to beam AB, in the direction parallel to beam AB, okay? Parallel meaning I have reinforcement this way, okay? Think of it, this is one-way slab, so I have a shorter span going in this direction and longer span going in the other direction. And then I say this will be the longitudinal direction and this will be the transverse direction. So if I'm asking you the reinforcement along AB, which is transverse reinforcement, you immediately know that this should be shrinkage and temperature, okay? While reinforcement parallel to beam AC, which is this direction, is gonna be a longitudinal direction, and that is gonna be for flexure. So C is the correct answer. So this one definitely might be on the exam, okay? Might be on the exam, all right? Now, for the slab shown in problem 1A, which is the following grade 60 reinforcement configuration satisfy the ACI code requirement for shrinkage and temperature reinforcement? Okay, so basically it's asking you to design for transfer direction and pick out a reinforcement. So this one on the exam, okay, on the exam. All right, so moving on, let's go back to here. For a precast concrete beam that is not exposed to weather or in contact with ground, this is asking the minimum cover, and this one we covered in the first exam, so we'll not ask you this. Now this is flexure, we've done this before, so no more, okay? Determine modulus rupture, we've done this before, so no more. Time-dependent factor for sustained load, CE for 12 months load period, right? T equal to 12. Now remember, there may be a table we showed the other day, remember, and they are capped at 2.0, and the y-axis is CE, x-axis is actually time, right? There are 3 months mark, and there's a number here, which is 1.0, actually 6 mark, 1.2, and 12 months, 1.4, maybe, perhaps, go back to find it out, okay? So use that table we provide for deflection. This is O in deflection, okay? We just talk about it. And then you can find out this Cassie number, okay? And keep in mind, this is only Cassie, okay? This is only Cassie, not lambda. What, Bob, what do you mean by that? Well, lambda equal to Cassie on the top is a function of time divided by 1 plus 50 rho prime, where rho prime is the compressive reinforcement ratio, remember? So we're only asking for Cassie, we're not asking for lambda, okay? We're not asking for lambda. All right, okay, so that is that problem, and I'll say this is definitely on the exam, okay? Definitely on the exam. All right, 1H, a two-span, oh, whoa, two-span, okay? Open up two-span, prismatic, reinforced concrete slabs built integrally with support, shown in the figure below. Now, there are several tables in the moment coefficient lecture notes. Matter of fact, I took that from previous lecture notes, and there are few figures, right? If you look at it, there's a 2 or more spans in the first figure, okay? And lo and behold, in the bottom, or in the one figure down, there's a 2-span figure. And you may want to refer to that 2-span figure, okay? You may want to refer to that 2-span figures, okay? Not the first one, not the first one. But anyway, so choose a different figure, and this is different joint. So think about the 3 rows we talk about. For this one, you don't have a whole lot of choice, okay? This one, you don't have a whole lot of choice, all right? Anyhow, this one is 2 spans. We most likely will not have this. In the exam, you might see 2 or more spans, okay? You might see more than 2 spans. In the exam, you might see more than 2 spans, okay? Remember that. All right, so this one, I would say will be on the exam, but definitely not 2 spans, okay? More than 2 spans, okay? More than 2 spans. All right, so next problem. For a slab shown in problem 1H, this one, using ACI moment coefficient and computer design moment for interior support, the value of length supposed to be what? This is asking you to find a clear span. Where is actually a clear span? I'm finding interior support. Interior support is right here. Let me clear this up. Interior support is right here. So either C or D, okay? And I'm asking to find the interior length. So this is 11 feet of clear span on the left, 11 feet of clear span on the left, and then 12 feet of clear span on the right. And I am asking you guys to find the span length for interior support. That means you are sitting on 2 sides of it. Now, which one is the right one? You are going to use average. So 11, 12, average is 11.5 feet, okay? So this one definitely on the exam, definitely on the exam. Okay, all right, so that's that, all right? Next one, deflection, right? This one I have talked about during the exam. Like I said, IG, IGT, ICR will be given, so you don't have to worry about it. And MCR is cracking moment, need to know that. How to calculate IE, need to know that. ID, need to know that. IL, need to know that. Total deflection, need to know that. I went through this during the lectures yesterday, and the deflection lectures, okay? So make sure you go over that and understand how this is done, okay? All right. Last but not least is the column design, We haven't talked about this, which we'll do that during tomorrow and also Thursday. And I'll finish, once we finish the column design, I will drag this problem out again and discuss with you. Now note that in a previous year's exam, I have 2 problems, 2 column problems, okay? But for this year's, I may only have 1, and I remove the word may. I will only have 1 column problem. I say this again, we'll only have 1 column problem, okay? All right, well, that's actually a fast to go over, okay? So this will be the problem you'll be seeing in the final exams, okay? And like I said, the column problem, we haven't talked about it, which we'll do tomorrow and Thursday. And the column is really straightforward. And I will drag out these problems again after we talk about the column problem. And you will see 1 column problem in the final exam. All right. With that, I finish what I have in mind to talk about, and now open for any questions. Thanks. Folks, any questions for me? Anything not clear? Worried? Anything? Quiet? We all good?
No questions for me.